Okay, so one of the last sections in chapter 10 of our textbook, Gary talks about two series factorials. And I'm going to pay some special attention to this precisely because this should remind you of a certain experiment that we're planning, right? That we're working on right now, I should say. And I think it might help you in your analysis and thinking through the results of your analysis as we finish up our Ultimate Tomato Challenge throughout the course. So, two series factorials are just a plain old factorial, but where all the factors have two levels. So we're already very familiar with this in this course. In our Ultimate Tomato Challenge, we have the heat, which is high and low. We have the light, which is high and low. And then we have not a high-low factor, but a variety factor. It's just one variety or the other. And so this is very, very similar to what he's calling a two-series factorial. If we have k factors, where k, like in our Ultimate Tomato Challenge, we have 3 factors. Well, here we're generalizing it to k. We can use the shorthand of a 2 to the k design. These are really common. I see these all the time in engineering. In fact, I know we don't have any engineers in the class right now, but in engineering, you see these quite often. A 3-series design is where all the factors particularly have 3 levels. It's abbreviated as a 3 to the k. Again, another common one that you'll see in areas like engineering. A 2 to the k design is the smallest possible k-factor design because we've just got 2 levels. You have to have at least 2, right? They're very popular. They're used all the time, like I said. Some specialty notation and methodology is used for these just because of their popularity and generality. Gary mentions that often those factors are low and high, but they don't have to be. In our Ultimate Tomato Challenge, of course, 2 of them are. Okay, one of them is just one variety or another. So let's think about this notation. There's 2 general ways. He talks about this in a little bit more detail in the textbook if you read that section. Let's say we have k factors. Let's just illustrate it for 3 factors, he says. So we call these generically A, B, and C. You can think of these as heat, light, and variety. So we have 8 possible treatment combinations. We've already enumerated that in class for our tomato example. One method for labeling the treatments is to use a 0 if the factor is low and a 1 if the factor is high. Thus, for example, if we had A low, B high, C high, the analysis notation would be 0, 1, 1. We haven't been using exactly this notation. However, because we are using our factors as indicator variables in our model, we are essentially doing this. We just haven't used specifically that kind of way of denoting the factors. But if you like to do that, feel free to start doing that now. There's another method that he talks about also in the book, uses the lowercase factor if the factor is high and omits the level if the factor is low. He says this is more common. I don't have an opinion about that. I don't see this in my practice, but that just be my experience rather than his. So if, for example, we have A low, B high, and C high, this method this method would use the label BC. A is left out because A is low. I don't like this because I would think if I was teaching it this way, I'd think half the class would think when I gave you that notation, I said, oh, we're entertaining the BC factor, that you'd get that confused with BC interaction. And this is not BC interaction. This is the case where B is at the high level, C is at the high level. So we have the main factor for B, this main factor for C, and the interaction for C. And so I take issue with the second methodology, and I don't know, like I said, if it is truly more common or not, I don't care. I don't much like the notation. Here's kind of a standard way things get laid out. Again, we might emphasize this, but let's compare everything across so we make sure we understand both notations. 0, 0, 0 mean all factors A, B, and C are at the low level. That's equivalent with just the mean model, the overall global mean model in the second notation using 1. Remember, that just is the notation for the intercept. If we have 1, 0, 0, that second line in the table, that's just factor A being high, everything else low. So notice we have no interactions in this case, nothing else. Similarly, B is high here, so we have just B here. Let's skip down to this line. C is high here, nothing else. So we just have C here. Now we start getting into the models that include interactions between the terms. So here we have A is high, B is high, C is low. So this notation would just use little a, little b. I like this better because that makes it clear that we also have interaction. Similarly, AC, BC, or ABC is 1, 1, 1. In these models, each effect, main or interaction, in a two-series design has a single degree of freedom. You've probably already noticed this in the Ultimate Tomato Challenge. And so each effect can be determined using a single contrast, right? And it would be a type 3 by definition. So we can represent these contrasts as a table of pluses and minuses, plus ones, minus ones if you prefer. If we know the signs for the factors, we'll get signs for an interaction effect by the element-wise multiplication of the signs and the factors involved in the interaction. So let's see this played out, okay? The overall global mean model, 1, using that other notation. That would be 0, 0, 0, 0, using the notation that I kind of prefer. This would be a negative for all of the main effects because none of them are included. Everything else would also be negative. Here we see the model A, where model level A is high. B and C are low, so they get the negatives. A gets the positive for high. Think about A times B would be a positive times a negative, so a negative. A times C would be a negative. B times C would be a positive. ABC would be positive, negative, negative, so you get positive. Interesting, okay? Make sure you understand why that's true. You can go through each one of these. I don't think I need to go into any more detail. It's pretty straightforward, down to the full factor, 3-factor model ABC at the end, where everything is high and everything's positive. All of the effect contrasts in these cases are going to be orthogonal by design and also independent when you've got normal data. Under the null hypothesis of no effects at all, the contrast values are going to be independent with a mean of 0 and a constant variance. So things are pretty clean. That's part of why people like this kind of design so much. Significant effects are going to be outliers in the normal probability plot. This will assume that most effects are null and only a few are active. We call this effect sparsity in statistics, and it's a reasonable thing a reasonable method, I guess I should say, to go about this when we have single replication of all treatment combinations and hence can't estimate our pure error in the experiment. Outliers can be difficult to define. He quotes a famous saying of a Supreme Court justice in the United States. You may have familiarity with that or not. I have it kind of cut off. There we go. Lowered my screencast area. I'm not going to talk about that in class, but sometimes his point is sometimes it's hard to find outliers. There is a method. I don't know this method very well and haven't really used it, but it's one of the many methods we have for finding outliers. It's called Lunt's pseudo-standard error. I know Lunt's method for power calculation in mixed models, but I'm not familiar with his method here. But you can read through this and might want to use this at some point in the future. I'm not going to emphasize it in class, however. Okay, so this basically concludes factorials for us in class. I will get to a power analysis for a factorial model. Maybe I'll get to making the video today, or maybe we'll just treat it in class next time. See you then, and make sure you bring your factorial analysis for the Ultimate Tomato Challenge. Many of you have brought it or sent it to me outside of class, which is great, but we will be discussing it in class.